Today, we're going to talk about buffers. A buffer is a solution that resists changes in pH by neutralizing any acid or any added base. Now, most solutions change pH rapidly upon the addition of an acid or a base. And buffers resist these changes in pH by neutralizing the added acid or the added base. A buffer is made up of a significant amount of both a weak acid and its conjugate base. For example, here a buffer is made from carbonic acid H2CO3 and its conjugate base HCO3. When we add a base to this solution, the base represented here by OH minus would react with the carbonic acid H2CO3 and then forms the conjugate base HCO3 plus water. On the other hand, if we were to add an acid to this buffer, then the H plus ions from the acid would react with the conjugate base HCO3 minus to form carbonic acid H2CO3, thereby preventing a large increase in the pH of that solution. The acidity of blood is critically important, and it is tightly regulated within the human body because many proteins require a narrow pH range for proper functioning. In human blood, for example, pH is held between 7.36 and 7.42. This almost constant blood pH is maintained by buffers. One important buffering system used in the blood is a mixture of carbonic acid H2CO3 and bicarbonate. Buffering capacity. The maximum amount of acid or base that you can add to a buffer without causing a large change in pH is called the buffer capacity. Titrations. In an acid-base titration, we typically add a basic, or it could be an acidic solution of unknown concentration with an acidic or basic solution of known concentration. Usually, the known solution is added slowly to the unknown one, and the pH is monitored either by a pH meter or an indicator. In this case, we are adding the base to the acid until the reaction is complete. The indicator allows us to know based on color that the reaction is complete. As the acid and the base combine, they will neutralize each other at a point which we call the equivalence point. Here we have a graph showing the strong acid and a strong base titration. And what this graph shows is as the base is added slowly to the acid, the pH slowly rises until it gets to a point where the amount of OH ions is greater than the amount of H plus ions. Midway between that rise is what we call the equivalence point. This is the point in the titration where the number of moles of base is equivalent to the number of moles of the acid. And this is where we say our titration is complete. Notice that pH changes rather quickly near the equivalence point. Beyond the equivalence point, the solution becomes basic because all of the HCl has been neutralized. This is the profile of a typical strong base, strong acid titration.